For our 201 class, I wanted to walk through the lecture 3. I've added some slides at the end. I'm hoping everybody will be able to go through this presentation. It's meant to supplement what we've discussed in class. So what we've seen is that we're now talking about combinational logic. And in our combinational logic, we are talking about variables. We're talking about functions. We talk about inputs and outputs. So the variable is just like it is in algebra. The differences, our data type for now are just bits. So they're all 1-bit entities for the most part. At the end, we'll get a slide. We'll see where we could have a multiple bit variable that we'll refer to as a vector or perhaps a register. And we've seen that what we're doing is defining functions, just like the way functions are done in our typical algebra, be it add, subtract, multiply, divide. Now we're going to have a new set of functions. So our new functions we could call our building blocks. In this case, we refer to them as gates. And what they do, they impose a binary logic type of functions. And what they do is that we'll have inputs to our gates, we'll apply the function that we're implementing, and we'll generate an output. So like I mentioned, just like before, when you learn mathematics, the add function has inputs, be it in this case, example has 8 and 7 as an input. The output is 15. We'll talk a little bit about a left to right flow. You could abstract this as y is equal to the addition of 8 with 7. So here is the output, here is the function that we're implementing, and these are the inputs. The functions that we're talking about now are logical functions. You'll find them in a formal logic class. But the ones we're referring to are referred to as not, also called inverse or invert complement, the and, the or, the not and we call the NAND, the not or we call the NOR, and the exclusive or. So the first one being the not or the complement is fairly simple. What it does is when we apply an input, we've said our inputs are scalars, so it's either a 0 or a 1. If we input a 0, the output will be a 1. If we input a 1, the output will be a 0. Here we see the Verilog proper expression, y is equal to not x. So this is the bitwise negation operator that we'll use when we get into programming Verilog. Now what I didn't discuss in class, but we must take a moment now and look at, is once we've learned the not operation, now we can consider how to not just a scalar, but how to not a vector. So in this case, consider a vector with a value 101, 101, 00. If you wanted to generate the complement of that number, what that means is that every place there's a 1 in that number, it becomes a 0, and every place there's a 0, it becomes a 1. So in this case, we started with 1 0, 1 0, 1 0, 1 0. The 1's complement would then be 0 1, 0 1, 0 1, 0 1. The 2's complement is an expression that we'll use later on when we're implementing our arithmetic operations using logical gates, and the 2's complement is similar except that it's the 1's complement with a 1 added to the value. So if I add a 1 to this value, of course this is going to be a 0, I carry the 1, so 0 1 0 1 0 1 1 0, and that is the 2's complement. File that away, we'll use that coming up pretty quickly. The AND operation, we read when x1 is a 1 and x2 is a 1, then y is a 1. We express it with this type of expression. We use the ampersand as the AND operator. With the OR, it reads a little differently. Now it reads if x1 is a 1 or x2 is a 1, then y is a 1. We can express it using the OR operator from Verilog as y is equal to x1 or x2. The only qualification here is that the OR in this case is referred to as the inclusive OR because it includes the case where both of the inputs are a 1. So if either are 1 or both are 1, the output will be a 1. The NAND is the not AND. The way it works is if both inputs are 1, then the output will be a 0. If either of the inputs are 0, the output will be a 1. You can express it as there's no NAND operator, so we say it's the not of the AND. The NOR is similar, except now we're implementing a not OR, and the same is true. If this is a 1 or this is a 1, then the output will be a 0. We express it with the same type of nomenclature. Since we don't have a NOR operator, it's a not OR. And the parentheses help force the association to perform the OR first, then negate the result. The exclusive OR is a little bit different, but it's similar to an OR in that if either x1 or x2 is high or is a 1, then y will be a 1. The difference here is in this case, if they're both 1, the output will be a 0. So again, here is the expression using the hat, or you could say that guy shift 6 as the operator. Another way to look at this with a 2-input exclusive OR, if the 2 inputs are the same, the output is a 0. If the 2 inputs are different, the output is a 1. We've mentioned that it's possible to have gate operations that have more than 2 inputs. The way that the exclusive OR works is, let's say there's 5 inputs instead of just 2. The output will be a 1 if there are an odd number of 1s on the input. So, like I said, assuming this was a 5 input, if the pattern was 1 0 1 0 1, that would be 3 1s, the output would be a 1. If the pattern was 1 0 1 0 0, that would be an even number of 1s, and the output would be a 0. How do we define the behavior of our gates? We use truth tables. And the truth table nomenclature is used a lot in our world. Down below, what we see are a couple familiar operations, be it an add or a multiply. On the left-hand side are the inputs. Then on the right-hand side would be the output of the operation. So if I'm adding them, of course, it's a 9 or an 8 or a 13 or a 10. If I'm multiplying, then it's 20, 15, 42, 21. Now, when we look at our logical operators, now our operands are bits. So there's only 4 possible patterns for 2 inputs, 0, 0, 0, 1, 1, 0, 1, 1. And now we can document the behavior. So the AND is only true if both are a 1. Every other case it's a 0. The OR is true if either or both of them are a 1. So the OR is 0, 1, 1, 1. So keep in mind when you look at a truth table what you're looking at. The left-hand side represents the inputs. The right-hand side represents the outputs. For us, for our logical operations, our inputs will always have every possible pattern, as opposed to here where we were demonstrating the set of real numbers or the set of even of integer is too large to be exhaustive. So this set you would say is representative. Here, this set is exhaustive. There are no other patterns that I could present using two inputs than 0, 0, 0, 1, 1, 0, 1, 1. So in doing that, I've completely defined the operation of our gate. So I mentioned in class, the functions may be considered a black box. There's something going on in there. We don't know exactly how they're doing it, but the inputs are being applied. The flow passes through the box and the result appears on the output. Now we've seen this could be an and, an or, exclusive or, it may even be more complicated than that. This is the page that everybody should commit to memory. Everybody should know the operators that we will utilize to define these operations. Please keep in mind that these operators are not unique to Verilog, but Java, C++, Python, they use the same operators to implement the same functionality. Then on the right hand side, I've used one truth table to define all of the basic gates. The and, the or, the not, in which case I have to specify which input I'm complementing because it's only a unary operator. Exclusive or, nan, nor, and what I've included here is a buff. And this is just for thoroughness. The buff passes the value straight through. So if A is a 1, Y is a 1. If A is a 0, Y is a 0. Normally we use a buff if we're trying to change a signal name or there's some other electrical considerations. But for us, the buff is similar to the not, except that with the not, the output is complemented. With the buff, the output is the same as the input. This page also you should commit to memory. You should be able to draw an AND gate, an OR gate, the NOT, the NAND gate, the NOR gate, the exclusive OR gate, and the buff. Please keep in mind that with the AND operations, the back side is flat, then we have a round. With the OR operations, the back side is rounded and the right hand side or the output comes to a point. A better symbol would have been having this come to a discrete point, but I couldn't find them when I was drawing them, so this is pretty close. Then what's unique then with the exclusive OR, and you can see it comes a little bit more to a point here, is that there's the second curved portion on the back to differentiate this from this. We discussed a little bit in class how we can read our symbols, and we talked about how the bubbles indicate an active state of 0. So in this case, we would read if this input is a 1 and this input is a 1, the output is a 0. Here we would read if this input is a 1 and this input is a 1, then the output is a 1. Now, we'll learn about De Morgan's laws, but it's basically a graphical technique that it's not bad for us to understand today. This gate behaves exactly the same as this gate. It's logically equivalent. It just is representing a different function. Here we said if this is a 1 and this is a 1, the output is a 0. Here we're saying if this is a 0 or this is a 0, the output is a 1. Same thing here. This is the AND gate. All the inputs are high active. If the only time the output is low is when either of the inputs are 0. So I say if this is a 0 or this is a 0, the output is a 0. So this is called De Morgan's law. The technique is where there are no bubbles, you include bubbles. Where there is a bubble, you don't have a bubble. Where you encounter an AND operation, you replace it with an OR operation. We'll talk a little bit more about this in class. Here, this chart, you can look at it, and we talked about the synonyms between high, low, 1, 0. Basically, I'm discussing here how to read and interpret these. That's an AND operation, an OR. This tells you if this is a 1 and this is a 1, that's a 0. So you can read this chart. Once we have the behavior of the gates within our grasp, now we can begin to create more complex functions. And we do that by combining them together, and we can document their behavior using a truth table. So in this case, here's a very simple little circuit. You can see it's comprised of 4 gates: an AND gate, a NAND gate, an OR gate, and an inverter. There are 3 inputs, which correspond to the 8 rows in the truth table. And the way that we would analyze this type of circuit, it's nice to give intermediate names to the connections. And then we can say, oh, since the inputs are given when we're doing the analysis with 3 inputs, 2 to the 3 is 8, so we have 8 rows. So now we could come through and we could generate I1 independent of everything other than A and B. So we know I1 will be a 1 when A is a 1 and B is a 1. So we come down our truth table, and it's only once A is a 1 and B is a 1, I1 is a 1. When A is a 1, B is a 1, I1 is a 1. Now we look here, now we have B and C contributing to I2, and we know it's only if this is a 1 and this is a 1, I2 will be 0. So now following down through B, C, here, when they're both 1, I2 is a 0, and we have that case one more time here, I2 is a 0. Every other case, I2 is a 1. Now we have a simple OR gate, so now we can look for each row in our truth table, and we say if I1 is a 1 or I2 is a 1, I3 will be a 1. So here I2 is a 1, same. Here I1 is a 1. I think I made a mistake here. So let's check it out. I1 is a 1, I3 should be a 1. I'll fix that on the slides. So that should be a 1, that would be a 0, and then we'd see in the end there's only one case Y is a 1. It's when all 3 of these guys is a 0. So hopefully this helps. You can walk through it. Hopefully the teacher doesn't have too many mistakes in what he presents. Now once we have that, we can build our simple circuits. One of the first circuits that we're going to learn and we're going to deal with in our next lab is the multiplexer. The multiplexer is also called a data selector. It's similar in notion to a switch. On the right is a diagram representing a switch, where we have 2 inputs. And as you move the switch from input to input, the output will represent one or the other. So that is a switch. Here, the multiplexer, we have a select. When it's a 0, I0 shows up on the output. When there's a 1, I1 shows up on the output. So this is a multiplexer. We're going to use these a lot. So this would be referred to as a 1-bit wide. So the data path is 1 bit wide, 2 to 1 mux. Since it's 2 to 1, we only need 1 select bit to choose between the 2 inputs. How do we build a multiplexer? A multiplexer is constructed, and we'll do this in our lab, by using inverters, AND gates, and an OR gate. And the A is the select in this case. So when this is a 0, this will be a 1. So when select is a 0, x0, and this will be here. So what will be here will be the value on x0, and that will show up on x. When A is a 1, this is a 0. Now the other gate has a 1. So whatever value is on x1 will show up at x. And if you study the truth table, that should tell you. So when A is a 0, whatever value is on x1 shows up on x. When A is a 1, whatever value is on x0 shows up on 1. X. So the number of inputs as far as the select is always a power of 2. The number of bits are always a power of 2. So here now we have a 4 to 1 mux, in which case we'll need 2 select bits. And the 4 patterns, of course, would be 0, 0, 0, 1, 1, 0, 1, 1, selecting different AND gates to let the patterns pass through. This is what we would call a 1-bit wide 4 to 1 mux. It's possible to have a multiplexer that passes n bits at a time. In this case, this diagram is showing us again a 4 to 1 mux. We have our 2 select bits, select 1 and select 0, giving us the 4 patterns, 0, 0, 0, 1, 1, 0, 1, 1. And then we have our 4 data options, in this case, each of which is 16 bits wide. So if this is 0, 0, what this means is the pattern that is on data 0 will show up on the output. If we switch this to 0, 1, then the pattern on data 1 shows up on the output. So this is referred to as the data path. We'll see this is the control. This is what is choosing how this multiplexer should operate. Another basic operation is the decoder. And what it does, the decoder is a circuit that will decode an input so that the output identifies the pattern that is found on the input. So here I have 2 bits on my input, which I can have 4 different patterns, 0, 1, 2, 3. The way this decoder works is that the pattern that is here will cause the associated output to be high. So if this is 0, 0, D1 will be high. So if it's 0, 0, D1, 0 is high. If it's 0, 1, D1 will be high, 0, 1, D1 is high, and so on. So this is called a binary decoder. In this case, it would be referred to as a 2 to 4 binary decoder. I believe the last slide here adds I'm trying to get this up so we can see it. There. So now we have a decoder, but this time with an enable. In this case, it's a 3 to 8 binary decoder with an enable. What this means is that, and you can study the right hand side, but I'm going to just walk you through it here. If the enable is a 0, because we know it's high active because there's no bubble here, if it's a 0, that means the decoder is disabled. If the decoder is disabled, that means all of the outputs are 0. Now, if the enable is a 1, now the decoder is able to function, and the pattern on the input will cause the associated output to be high. So if this is a 1, all three of these guys is 0, then output 0 will be a 1. If this is high and the pattern here is 1, 0, 0, which is a binary 4, then output 4 will be a 1. All of the other outputs will be 0. So hopefully this helps. I'll chat a little bit about this in class, but I would encourage you to walk through and make sure you're comfortable, in particular the things I tell you you need to memorize. Please do so.